much, everybody. We're going to talk about web handling tensioning, and we're going to use a couple of products from MapleSoft, both MapleSim and MapleFlow. And here's what we're going to cover, basically, in this next hour. To get started, we need to, in the context of webs and web handling, define what stress and tension and strain and modulus means for webs, because they're the fundamental aspects we need for understanding how webs are transported. The next concept is the constant mass flow rate idea and the strain transport formula. We'll dig into that. Then we're going to talk about how does a web converter determine what are sort of the lower and upper limits on web tension that you may need. And then we're going to finish with a series of simulations showing different methods for controlling tensions. So first of all, just a basic idea, and this is just from engineering, the concept of stress applies to webs as well. We have to pull webs through machines. You can't push them. They're like a rope. You can't push them. You have to pull them. So you have to apply a force, and that force is applied across its cross-sectional area, which is thickness and width. And for webs, the thickness is usually, well, it is always much, much thinner than the width or the length. The force that is applied to the web, we call tension in the context of web handling. So it has units of force, newtons in SI or pound force. And then sometimes you'll see the tension divided by the width of the web, the relaxed width, so that you see units of force per width. So if you divide by the width and the thickness, you end up with units of stress, which is in pascals and SI or PSI. And you see an example there on the screen, just of one case where there are 14 newtons of tension on a 200 millimeter wide web with a 25 micron thickness. You see the number of pascals involved in that. And these stresses, in the web itself, when you then wind these webs up on rolls, which is a common way of packaging webs that are made, or in wound rolls that you unwind, the tension that's in the web is converted into two different types of stress, at least two types in the wound roll. First is radial stress, that's kind of pressure between the layers, and tangential stress is the machine direction stress. So you see a couple of plots on the page there showing for one particular set of winding conditions and material properties, this radial stress or pressure is often highest at the core, is usually highest at the core, and then in this case it plateaus and then falls off on the outside. The tangential or circumferential stress, even if you're winding a constant tension, that circumferential stress is not constant in the wound roll because the compression of the layers changes that stress. So why is tension then important? Why are we even talking about this? Well, it affects so many things in web handling. It affects whether you're going to have wrinkles in your web, if you're going to have curl in your laminates. If you have webs that were made such that the length of the web across its width is not the same. You may have baggy or loose lanes or edges. Tension affects whether you will have traction between the web and rollers. And as I've already talked about, the wound roll structure and defects are affected greatly by the tension of the web going into them. Tension's important in avoiding damage to your material. Typically, the goal of web handling is just to transport webs without any damage or loss. And if you overdo the amount of tension, you could yield the material, changing its original length and nature. If there are edge cracks or tears, you can make them worse and even leading to a complete tear out or breakout of the web. And then many product quality aspects are affected by tension. If you're printing webs where you're trying to lay multiple colors down on top of each other in successive print stations, if you're not controlling the tension, you won't control the position of the web affecting the print. Tension affects the slit width as well. And then guiding the web or steering the web laterally into processes that matter, like coding, are affected also by tension. So we need to control it well. A related parameter, when you apply tension to a web, you will change its dimensions. And so this is sometimes referred to as strain, where you have an initial length of a web, a relaxed length. You apply tension to it, it will deform, it will lengthen, and you'll end up with a percent change or a change in length over the original length. And that's the strain. So related to that is a parameter called Poisson's ratio, which is simply that you've applied tension to the web. Some webs typically will neck down, as it's called. They'll change width and shrink in the cross machine direction. And the ratio of that lateral strain to the longitudinal strain is Poisson's ratio. For many webs, especially high modulus, we'll talk about modulus later, but high stiffness webs will have a lower, typically, Poisson ratio of around 0.3. But certain fibrous webs, like nonwovens, can have very high Poisson's ratio approaching 1 or even over 1. And the last sort of material property related to tensioning is this modulus of elasticity, which it's basically the slope of the stress strain curve. And you can measure this modulus in the machine direction or the cross machine direction. You can do it on tensile testers with small samples, or a very low-tech way is to use a very long web sample, tape it to the floor on one end, mark a distance between two marks on the web, attach the other end to a force gauge, pull on the web with different forces, and measure the change in length. And then you'll have the tension and the strain, and you can calculate the modulus from that. And as an example, I'm going to switch to another screen. Hopefully you can all see that. And this is a product, MapleFlow. It's like kind of a calculation sheet. And this is an example of data from a modulus test. So I pulled some web on the floor, got changes in length over original length. That's what these strain values are. And I have the force divided by the width of the web and the thickness. And so I've got stress values. Then using this software, I can plot the data points, and you can see stress on the y-axis, strain on the x-axis, and it looks approximately linear. So then we can use this software to fit a line through the data. And in this case, I forced it through the 0, 0 point. And so the slope of this line is going to be the modulus. So here it is in pascals. And then you can see the plot here of the best fit line against the data points. So switching back to our screen, we now switch to the basic concept first of constant mass flow rate. So when I was in chemical engineering school, we learned a lot about fluid flow in pipes, and one of the first equations I recall was this continuity equation, which is that fluid in pipes will change their velocity to keep the mass flow rate constant. So if the fluid goes through a constriction, it will accelerate to a higher velocity to keep the mass flow rate the same. It's conservation of mass, basically. And there is an analogous formula called the strain transport formula in web handling, because it did the same way. When you feed web into a web converting line, you have to take the web out the same amount of mass, unless you have some accumulation, which would mean web on the floor, or you try to take out more than you put in, you're going to eventually break the web. So this equation here, this velocity over 1 plus the strain, turns out then to be a constant at steady state for the mass flow rate to be the same. So you can calculate then, we know the tension and strain are related by the modulus. So you can calculate the strain from tension and modulus and width and thickness. And you can manipulate that formula to show that if you know a reference tension or velocity in one position on the machine, you can calculate tension and strain in other parts of the machine. So I'd like to show an example again in MapleFlow. And this is an example from a paper by Ron Lynch, former colleague of mine. And he shows a web handling system here that is simply an unwinding roll through a series of idler rollers, one of which is a load cell. And then you see several knit rollers in succession, a V reference, V1, V2, V3. And we know the velocities of each of these rollers. They're fixed speeds. And then we know certain other things like the tension in the this first span from this load cell. We know the modulus of the web. We know the width of the web, and we know the thickness. So from this, we can calculate several things about what's going on in each of these spans. We can calculate the strain in this reference span from the tension in the reference span, the modulus, width, and thickness. So it's about 1.45%. Then using the equation from the previous slide, we can calculate then the strain and tension in each of these successive spans. So we can also, using this calculation spreadsheet, do some what ifs. We can say, what if the tension is only 8 newtons instead of 10? It will recalculate through the whole sheet and give us the change in tension and strain. Or similarly, modulus. If we have a lower modulus web, how will that affect these tensions and strains? So it's a useful formula for understanding at least steady state. And there's the example, and this was the summary. So we see velocity differences by span and tension and strain changes at steady state. So let's switch now into tension requirements. When we're thinking about what tensions should we have in our web converting process, the first thing is typically to think about the parts of the process that are the money makers for you, the value added steps in the converting process. Much of web handling is just transport. Transport to the operations like lamination and coding and printing and die cutting and slitting and winding that make the money out of the converting process. So those particular processes may have particular tension needs. And so those are the first things to consider. You may also have to consider that the web you have to convert is not perfect. I'm sure some of you have experienced that. And so some of these webs may have loose edges, loose lanes, and we need to be able to convert or transport those webs. Because webs are so thin, they wrinkle very easily. It takes very little stress to buckle them. So avoiding wrinkles is a key consideration in what tension you need to run, because there is a bit of a Goldilocks situation with tension. You can have too little, you can have too much. Both conditions can create wrinkle situations. And then, as we talked earlier, maintaining traction between revs and rollers requires a certain tension range. Too much and you'll slip, too little and you won't stay adhered to the roller. So let's talk first about the low limit end of things. There's a minimum tension just to maintain traction. There's a minimum tension if your web is heavy and it sags between rollers. There'll be a minimum tension you need to reduce that sag. If you have a web that is curved, and we'll talk about this more, curved or cambered, That means typically you'll see a loose edge on that web, and it will track to its loose edge in the machine. So there's a certain tension you may need to handle that kind of web. And then we will want a certain web tension to avoid wrinkling, because it provides some stiffness. So let's first talk about the capstan equation and the concept of traction. So this is a well-known equation. It's also called the band break equation or the belt equation. It basically says this is the tension ratio you can have around a roller without losing traction. And it's e to the mu beta in this case. You'll sometimes see beta denoted as theta or any other Greek letter you choose. But essentially, the coefficient of friction mu is a parameter that's unique to the web and the roller combination. It's not a material property. It's you have to look at both. And then the beta is the ramp angle. So if the high tension side, which can be upstream or downstream, exceeds this ratio, you will slip on the roller. And if the web is very heavy, then the equation on the right side of the page includes the centrifugal force with velocity and density of the web and thickness. Another consideration for traction is that you need a certain amount of force or tension on the web to overcome the bearing drag that's in idlers. And so typically the bearing drag torque, or what you have to do to overcome the bearing drag in idler rollers, is a function of its static torque or starting torque. And then many idlers exhibit an increase in this frictional resistance to rotation with an increase in velocity. And this equation is just a simple linear relationship. It can be nonlinear. So you can calculate the tension loss due to the bearing drag in this equation by knowing the starting torque and knowing your velocity. So there's a tension loss for each idler in a web path, with the tension to being lower upstream. And so you can calculate this bearing drag from what's known as a Spindown test. You can accelerate an idler roller up to a certain number of RPMs that are typical of what you would be running in your web handling system. And you time basically how long it takes for the roller to stop. And you collect RPM data during the deceleration. So we can look at an example of this. This is the typical test where you may have a device that raises the roller RPM, or even something as low tech as wrapping a rope around the roller and pulling on it. And then you measure the RPMs of the roller over time. And so you may get a plot like this. Eventually the roller will stop because the friction, the bearing, slows the roller down. So you may start off at 500 RPM and go to 0 in a certain amount of time, and that's the kind of data you can collect. So if you know things like the outer radius of the roller, the inner radius of the roller shell, and the density of the material used in that shell, the width of the shell, you can calculate the inertia. You know the spin down time from your data. You know the initial RPM. You can then calculate this roller deceleration, and the bearing torque is this inertia times the acceleration, and so forth. You can end up with then what is this bearing drag torque, or sorry, bearing drag force. So for example, if it took longer for this roller to spin down, we would expect, let's say it took 80 seconds, instead of 0.084, since it went for longer, then obviously it has lower drag. So that's just an example of the bearing drag. So why did I go through all that? Well, this equation from my colleague, again, Ron Lynch, shows that this minimum tension to maintain traction is a function of the drag plus the mass of the roller times its acceleration, say during a ramp up. And then in the denominator, we have this e to the mu theta or mu beta as it was in the previous slide. And so this example just shows that there's a minimum amount of tension of 0.24 newtons just to overcome the bearing drag force and to maintain some traction on that roller. Now, that coefficient of friction between the web and roller may be lower than you think if you have this problem with air entrainment. So a moving web and a roller both carry a boundary layer of air into this converging nip at the entrance of the web and the roller. And the tensioned web is exerting a pressure against the roller. So there's two different things fighting each other here. And if there is enough tension, you will get the asperities or the kind of the bumps and ridges and sharp edges of or sharp points of each web and roller. They'll start to interact and you'll get some frictional contact. But if you are going fast enough, if you have a big enough roller, if the tension's low enough, you can generate an air film height, this H shown on the picture, that can be enough to separate the web from the roller. This is analogous to hydroplaning your car on a wet road. And so you can get a little bit of protection from this, from the fact that the air may leak, some air may leak out the sides of the web. So for narrow webs, this may not be as big a problem. And also if the web is permeable, say it's like paper or non-woven, you may get enough air through the web, forced through the air that through the web that you will not get any loss in traction. So you can calculate this air film height, this H0. This is based on a foil bearing equation. And it has things like the web velocity, the roller velocity, web tension, and the mass of the web, or basis weight, and so forth. And that term in brackets, epsilon, since it has a lot of velocity terms in it, you can plot that and calculate what is your actual coefficient of traction. So in this plot, we show at 0, epsilon meaning that you have no air entrainment effect. You may have a static coefficient of friction of 0.4, but as you increase the speed, you may start to lose more and more of this coefficient of traction. So we have an example again in MapleFlow of this calculation where we've got our roller dimensions, we have the dynamic viscosity of air, our web thickness, width, density, etc. We could calculate this air film height, and this example was 14 microns. We have our tension at 1 Newton per centimeter. We have our air permeability of the web. We have roughnesses of the web and roller. Because if you build up enough of an air film height, you will separate the roughness regions, the asperities of the web. And yes, this gets a bit complicated. You don't want to do this by hand. But at the end of the day, using this math from Keith Ducote at Oklahoma State from his thesis, you basically can see that the actual coefficient of traction for this web is reduced from 0.4 to about 0.28. So what happens, say, if we reduce the web tension in half? What is going to happen to that coefficient of traction? Instead of 0.3, it is 0.15. So again, the tension helps with maintaining traction on the rollers. And there are the equations for this side leakage and for the air film height loss through a permeable web. This was our example with the various roughnesses and the inputs. And this was the summary showing the difference in traction as a function of the tension. But you could also in that equation put in different roller sizes, different velocities, play lots of what if games. So still on the concept of minimum tension that we need, another issue with webs sometimes is this concept of a cambered web. So if you were to take your web and lay it flat on the floor or on a table, a long length of it, if you have to curve the web, in order for the web to lay flat all the way across, then you have camber. This can sometimes be observed as a loose edge, or you may also see the web steer in the machine laterally towards the loose side. And there are many different causes for this. It can be that it was made this way because it had different thicknesses across its width, or it's been subjected to a temperature difference across its width that changes the coefficient of expansion. You can yield the web running it through different processes like embossing rolls, etc. But you can calculate a radius of curvature from this value D and the length of the sample. And then the best way to deal with camber is not to have it. It's not very helpful, but try to eliminate it at the source. But if you have to run a web with camber, tensioning it at a certain level such that all the sections across it can be tight or at least partially loaded will help you track the web. You'll still have a tension profile, but it may help. And this equation from John Shelton gives a calculation for a given radius of curvature and modulus and thickness and width. What is the minimum tension that you need to pull out that loose edge? And I think this is a fairly simple equation, so I don't think I'm going to switch to the MapleFlow for this. But generally, it shows you that as that radius of curvature goes down, meaning it's a tighter curve, it has more curvature, then you're going to need a higher tension to handle it. Another case you may deal with on the minimum tension standpoint is for webs that are, say, coated with very heavy coatings over long spans between rollers, you may see the catenary effect of the web sagging. And there is a formula here for the minimum amount of tension that you would need to not exceed a particular maximum allowable web sag. So it has the length of the span, the basis weight, which is the mass per unit area of the web, width, etc. So again, you could start to add up these various minimum tensions to know your sort of lower level need for tension. Now switching to the high tension design limit side. Again, we said that the purpose of web handling is to transport these webs without damage. So we want to stay below the yield stress and permanent set limits, and we'll talk about that. We want to stay below a particular stress that can create basically wrinkles in the material, troughs, they're often called in open spans. And we also want to not exceed that tension ratio that we saw in the capstan equation that will cause slip. So a review from material science is just this concept of yield stress. When you do these stress strain curves and you look at the plot, there's typically a linear elastic region up there to point A in this plot. And if you keep pulling the web with higher and higher stresses, you will see a change in the material where the modulus, the slope of that curve, starts to flatten out. And you can define a point where you will create essentially permanent damage to the web. If you were to unload it then and look at its length down there on the strain curve, it will not return back to zero. It will stay permanently longer. So you've created what's called permanent set. And this is not typically something we want to do in a web transport context. So there are rules of thumb for, well, how low should you be relative to your yield stress? It's basically how much safety factor do you want to have? Some report, say 10 to 25% of your yield stress is where you should be handling your web. But it depends completely on your particular web and what kind of stresses and strains create permanent damage. If you overtension a web, you can start to see longitudinal waves or troughs form, particularly around the center of the web. And if those are big enough and close enough together, they can then perpetuate through subsequent spans in the machine. So there's some equations for calculating, given a certain tension, what kind of wavelength and amplitude waves are you going to generate in your web. And from some finite element modeling, it's been shown that in one case, if you get a very high ratio of the amplitude to the wavelength, meaning you have very tall waves in the web and they're very closely spaced, then you're going to generate wrinkles in the web. So we can take these two equations again, and we'll go back to MapleFlow. And we can, in this case, this is for an isotropic web, meaning all of its properties in both directions are the same. And there's some photos here what I mean by troughs, these waves that form. And if they're particularly big and close together, then they can end up transferring on rollers and become wrinkles. So given a span length and a web width and a web tension, you can calculate the number of these troughs that are going to form, in this case 21. Now, from treating these webs like beams, there is a certain compressive stress before they will buckle, and that's called the critical buckling stress. And it's this equation here, which has span lengths and web thicknesses and modulus, the stress in the machine direction, Poisson ratio. So if your compressive stress calculated from this equation exceeds this one, you're likely to form these troughs. And in this example, it is just above the critical buckling stress. Then the equations for wavelength and amplitude can be calculated. And this is about a ½ inch wavelength and not a very high amplitude. So when we do this amplitude to wavelength ratio, it's below the 0.05 that typically would be a warning flag. So in this example, not too bad. So now we've defined kind of the basic properties of the webs: strain, tension, modulus, Poisson ratio. And we've talked about some considerations for upper and lower tension limits. So after you've determined sort of tension set points and upper and lower limits, the next question is, how are we going to control that? Do we need to control it? So I'm going to cover some examples now using MapleSim for various cases. A break to unwind where there are no control loops, a break to unwind with a feed forward control loop, and then a break to unwind with two different types of loops, feed forward, feed back. We'll talk about dancers, various types of dancers, and then we'll put it all together in a dynamic simulation of a longer web path with multiple tension zones. So for those who may not be familiar with this product, MapleSim is a Modelica-based simulation software package from MapleSoft, and they have developed a specific library related to web handling, which enables you to create virtual webs with various web properties and create spans, which are the basically the distances between web handling components. There are a variety of rollers that can be used in the system that are typical of web handling systems, like idler rollers, driven rollers, SRAP rollers, NIP rollers, etc. You can deliver web into these simulated web paths with unwind drums or winding drums Or you can also just define webs coming in or out of the system with various properties of velocity and tension. They've added components for simulating lamination of webs, so multiple webs coming together and changing the web properties post-lamination. And then there are several ancillary components, things like load cells that are used to measure tension, revolute and prismatic joints to simulate various dancer types. And we'll see examples of those coming up. So first, a very simple example. We have an unwind, and it has a brake on it. We have 3 rollers, and we have a sensor that can measure the radius of the unwinding roll. Downstream, we are able in the simulation to basically pull the web from 0 speed up to a given speed. And just a little simulation or an animation so that you can see the rollers start to move and the unwind is moving. And that's just a basic animation of the simulation. And the kind of outputs we can get, well, first let's talk about what does that look like in MapleSim itself. And so you see a series of components starting in the upper left here with the web properties. There is a brake here that is connected to an unwind drum. And there is a fixed braking force that's being applied to this unwinding roll. We have the drum radius, and we have 3 rollers. And then we have a ramp up of the velocity, whoops, on the outside. I cut to the end of the story too fast. And we have a tension sensor that can measure the tension in that particular span. So we run this simulation. It's like a cooking show. I've already cooked it. And here is the output of this particular simulation, or a couple of outputs. In the upper left corner, we have a plot of the braking force. And I said it was constant, and that's what it did. It maintained its braking force as specified. We see the drum radius in the upper right, and it's coming down, obviously, as the web is unwinding. The radius is reducing. This is over the 30 seconds of the simulation. Now the plot we care most about, and this is the tension plot in this particular system. And you see there was this 5-second ramp at the beginning, and that leads to a tension spike in that particular span. And then we have our reference tension here, but we notice that the actual web tension in that span is gradually increasing as the roll unwinds, which is not what we want. We would like it to stay constant, but we have no control in this system just yet. So what can we do? In this example, building on the last model, a feed-forward loop has been added such that the radius of the roll is being used to inform what sort of braking force should be used on the unwinding roll. So it's going to change with the radius of the roll, unwinding roll. All the rest of the simulation is the same. So let's take a look at how this comes out. Now you see the braking force is matching, at least in shape, the radius of the drum because of this feed-forward loop. And we see later in the simulation the difference between the reference tension and the actual tension. In this particular plot, you can hardly see the difference. If you zoom in on it, there's still, a 1% difference or so between the reference and the actual tension. And we see, however, there's still this tension spike at the startup. So we maybe can improve upon this situation. And now the final example here with this particular model, we see that now we're added a feedback loop from this tension sensor back to this controller. We still have the feed forward, but now we have a feedback that's also being fed to the braking force on the drum. So we have now both feed forward and feedback loop, a proportional integral feedback loop is now added. And what do we see now for the result? Now we see the braking force is not constant. It not only adjusts to this roll radius, but we also see this big drop in response to that initial tension spike. And we still see the drum radius reducing. But now, looking at the tension plot, especially out at the steady state, there is no difference basically between the steady state tension and the reference. And the spike has been greatly reduced. There's still a little disturbance at the beginning, 5 seconds, but it's barely perceptible compared to what we had before. So let's switch gears to dancers. And we're not talking about Dancing with the Stars here, but a component that's used in web handling that is very common. It indirectly controls tension, I'll put it that way. What it is you have a web under tension, and it interacts with some kind of a movable roller that has a starting position. Let's say the tension changes on that web, either because of a speed change or a material change. And a particular roller then will change due to the web tension change. Its position will change. Then there is a sensor, say a potentiometer or other type of sensor that will detect the position change of the roller and feed back that error to a drive or a brake. And then the torque or speed or the brake torque is adjusted. So there are various types of dancers. There are things like pivoting roller dancers. They're often loaded either by gravity or, say, an air cylinder under pressure. And it will pivot up and down given changes in the modulus of the web or web speed changes. There are translational dancers. These can be linear rails or guides, and the roller will move along a straight path back and forth. And then there are rotational dancers where the rollers will pivot about an axis or rotate about an axis more precisely. So let's look at some examples here. This is just a simple linear dancer simulated in MapleSim. And so the roller is moving in response to tension changes, and I'll explain why it's doing that in the next plot. This was the model for that simple system. So the moving roller itself is modeled with this prismatic joint. So it's a perfect linear motion up and down. The web going into this dancer is ramping up over 2 seconds. So it's being fed in over 2 seconds with a given tension and at a given speed. Then coming out of this dancer for 2 seconds, nothing happens until it is a 2 second web velocity ramp up starting at 3 seconds. So for about a second, nothing happens, and then this web will start up pulling the web out and ramp up over a 3 second period. So there are some tension dynamics from this movement. You see initially the first 2 seconds where web is feeding into that dancer, the tension is dropping. And then for 1 second, it's stable until the web is pulled out of the dancer, and you get an initial spike for 2 seconds while that happens. So this is showing some of the dynamics that can be modeled within MapleSim. The next example is this rotational dancer, and you'll see the color changing on the web sort of periodically. That's implying a tension change in the web. The color change implies that. So it's oscillating back and forth. Why? Why? Because in this simulation, we have a sinusoidal tension disturbance downstream. So we're increasing and decreasing tension up and down in this span here, which affects this tension in span 5. If we do not have traction on this roller, then we may see this oscillation in this upstream span as well if it slips here. This is how the pivoting dancer is modeled with a revolute joint. And this is how we feed the tension velocity into that dancer. So this is the output of the tension, and this is both tension in span 4 and 5 are overlaid on each other, and you see the sinusoidal tension occurring. And this is where we have any kind of feedback loop in the system. But now adding a PID control loop to this system where we are measuring the tension in span 4, and we're feeding that back to the torque on this dancer, then we can see the effect of that feedback loop, that PID loop, here in this plot. And we started this simulation, at 20 seconds. So after 20 seconds is when this PID loop starts. So for the first 20 seconds, we see the same oscillation. Then we have this PID loop kicking in, and you see the reduced variation in tension on span 4, because that is where the feedback is coming back from. There. Okay. Pivoting dancer. This is a simple arrangement of a unwinding roll. We have a spring-loaded dancer. We have a driven roller pulling the web through this dancer. Let's take a look at how that's modeled. Very similar to what we've seen before. We have this feedback loop on the dancer arm itself, back to the brake or the torque that's on the drive on this particular unwind. We have a ramp up of this driven roller so we can control its speed. And we have tension sensors in each of these spans, 1, 2, 3, 4, and 5. So we'll have 5 tension traces on this plot. And here you see the output. Because of the controller, we meet a steady state tension at about 5 seconds. You see it's sort of a first order rise up to that steady state, and you see different tensions in each span, and that's because of the bearing drag in each idler roller. So it's modeling this dynamic ramp situation. And this is what the brake is attempting to do to maintain, the feedback tension, desired tension in the dancer. So for our final example, we have put it all together here with a more complicated web path where we've got basically 4 different zones. We have a torque controlled roller, roller 3 here. We have a torque controlled nip here, and we have a nip that is speed controlled here. They all ramp up at different times. And so there's going to be dynamics affecting the tension in this particular span, actually all the spans, but we're going to focus on this tension in span 11 right before the final nip. But because they're all ramping up at different times, we're going to see different effects. So I'll run the animation and explain that first blue roller in the web path, R3, it's torque assisted, and it starts at 15 seconds into the simulation. The NR2, or that nip roller 2, it has a torque assist that happens starting at 25 seconds. And the nip that's pulling the web through the machine, S11, it ramps up in 10 seconds. So we have a lot of things going on here at different times. Not necessarily how you would want to design the path, but this is to illustrate some of the dynamics you can do. So this is the nip speed at S11. It ramps up in 10 seconds nicely. This is the torque on that first roller. It ramps up from 15 to 20 seconds. And this is the nip torque from 25 to 30. So what is the result of all that stuff going on the tension? Well, if we follow that tension in span 1, we see during the line ramp a spike, then a steady state period, then the roller 3 torque kicks in. We see a drop in the tension in that span. And then the nip roller 2 torque kicks in, another drop. So again, showing you a variety of dynamics going on in these systems. And so as summary, these are a couple of the products used to explore. This is obviously a big topic and we could spend much more time on it, but these are some of the tools from MapleSoft that was used to understand this a little bit more. So we'll come back to my contact information we need, but do we have any questions that I can answer for you with the time we have left?
Thanks, Steve. If you have questions for Steve, please ask them, type them into the Q&A, and then we'll just read them out live. Steve, it was really clear that you had a combination of the research that's been done over the years, building up these modeling techniques and these formulas that give you the safe thresholds. Was it possible to combine them into multiple roller models, or do you have to kind of treat each roller situation like as a small subset?
Well, as I showed on that tension zone example, I showed some fairly simple examples of accumulators or say single roller dancers or so forth, but very complex accumulators can be built up. For example, if I switch to another program, the actual MapleSim program. Sorry, don't want to use all our time up here. But for example, I'm talking and not doing this as I should be. Okay, here we go. In the help section, and hopefully you can see my screen, there's an example of an accumulator that is an example here that is a much more complicated set of rollers, as might be used in a dancer. And so we run the simulation for that. You'll see that this very complicated structure can move up and down as an accumulator would in a splicer. So yes, very, very complicated web handling, web paths with lots of dynamics can be built in. This shouldn't take too much longer, but you get the point that yes.
And the components actually look like the roller layout in the plant as well. So it kind of gives you that sense of connection for operators, right?
Yes, and it could be used as a training tool for operators in that sense, like a flight simulator, because you're able to do a lot of what ifs so that they can learn it in that situation versus on a machine. So they understand when they turn certain knobs what will happen versus doing that on a machine where you're burning up real raw materials and real time on a machine that might be worth something else, when you're actually producing. So yeah, so this is an example of this accumulator. Whoops. Well, this is not good doing this live, right? But anyway, I hope you see the point that we would get the tensions for this accumulator through its dynamics. So yeah.
We do have a question just come in. Can this simulate tension in a span traveling through an air flotation section in a dryer? Some of the process in the converting items can be a little bit more complicated. Do you have an insight on that?
Well, that's probably a question that could best be answered by your technical people, but basically there are air flotation devices like Coanda jet devices that float webs through machines, and there have been analytical equations developed for those kinds of things. One of the things I've done with this product is embed other calculations in the software. So if your air flotation physics of your device can be modeled, I think it could be coupled with the other tension elements in the web path. but I think that's a question to be answered probably by your developers. Yeah.
Well, and certainly with the MapleSim from my the technical team at MapleSoft, they are very committed to developing that as an ongoing relationship with the industry to make sure that there's, as new techniques and formulas are found, physics models, then they can be applied as soon as possible. We have another question. Will the simulation tool allow changes in PI values to help the control engineers zero in on the optimum values? So talking about the control pieces that you showed.
Yeah, yes, from what I'm not a controls engineer, but from looking into the guts, into the component blocks, those are, those gains, those controller gains are definitely inputs that can be played with. Because basically anything that's available, I believe, in Modelica for modeling controllers is available because this is built on that engineering language. So
right, and you had some simple ramp inputs, but they could very easily be some customized inputs that could be fed from another tool chain even. Yeah. Well, we're coming up to the top of the hour now. If you still have questions, then I would encourage you to send them in to us at MapleSoft. You can send them by email to webinars@maplesoft.com or reach out to any of the sales account teams that you may have come in contact with. I want to thank Steve again for such a great show. Took us through the theory, but also the practical applications that industry is setting, and it was really great to see that it just come to life with so many practical examples. So thank you, Steve, for your time today.